Okay, so here we are with the second problem dealing with bound charges, and we have a Teflon rod again, and this one has an inner diameter B, outer diameter A, and basically we now have a situation where we have the polarization is actually now equal to just K is a constant polarization. It's no longer a S-dependent polarization, and that's just in this region here, right? So between A and B, right? Sigma bound along the, let's say the A surface here is going to be P dotted with S hat when S equals to A, and that will be Ks dot S equals to K. Sigma bound B equals to P dotted with a minus S. Why is it minus S? Well, because anywhere along here, it's going to, the normal vector is going to be actually pointed in the minus S hat direction, right? So in toward the center of this thing, right? So that's the actual outer surface of this thing. So here we have again, that's going to be Ks hat dotted with minus S hat. That's going to equal to minus K. Okay, cool. What about rho bound? Well, I know that rho bound is equal to, again, minus the divergence of P, and that'll be minus 1 over S d by ds of S times K. It looks like that equals to minus K over S when we do take that integral and divide by S. Okay, so it looks like we have a now a bound rho, in other words, a volume charge density that depends on depends on S. Okay. So now let's take a look at the remaining things here that we need to think about. Well, there's a vacuum for either S is greater than A or S is less than B. This is a vacuum. So what does that tell us about P? Well, there's no matter. That means P has to equal to 0 in these regions, right? Okay. And what else do we want to say here? Okay. So we also have the symmetry situation, in which case we can use equation 4.23 in our book. So that's here, right? So remember that we're dealing, if we want to calculate D directly, okay, and that'll actually be in the second part here. When we want to calculate D directly, then we will need to just consider the free charges enclosed. So we'll get there. But for right now, let's take a look and let's find the electric field at all these different places here. So, well, let's see. Somewhat arbitrarily, let me just start with S is less than B. Okay. So here we're going to have E 2 pi SL. This is looking familiar. Equals to 1 over epsilon naught times the Q enclosed, right? Well, there isn't any charge for S less than B, so that's 0, and therefore E, let's say in region 1, is equal to 0, right? So I could do region 1, region 2, and region 3, something like this for the sake of our bookkeeping here. Okay, so E 1 is 0. Okay. Now let's get on to something a little bit more interesting. What about the situation where S is bigger than B, but it's less than A? So that's anywhere in this region 2 here, right? So region 2. Again, I have E times 2 pi SL, and that's equal to 1 over epsilon naught times, it's going to be a contribution from the inner surface here, right? That's going to be sigma B, right? And then we'll have also something from rho, So let's put that together here. So we have our sigma b. I'm going to ignore the bound part, but it's this part here on the inner part here, because that's going to be inside of my Gaussian surface, times 2 pi bl. Okay, now why? Because that's the surface area of this thing, right? So charge per unit area, and here's the area. And then I'm going to add the integral of rho of r prime d tau prime, and this is a volume integral, right? So it's a volume, so triple integral, and this is going to be my contribution, and I have to kind of be careful with this one because there is an s dependence, right? So rho bound is minus k over s. So let's be careful with that one. So I'm going to do this integral out completely here. I have a 0 to L, a 0 to 2 pi, and a 0 to some s. And I have minus k over s, ds, d phi, dz. That's my whole integral, and I should do prime, 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 and that's not prime, right? So when I do this out here, it looks like I have an s prime and an s prime, so I just have a constant. So that's going to give me, it looks like a minus k times, and actually, I just made a mistake here. So not from 0, but from b, right? So s minus b. And this is going to give me a 2 pi. This is going to give me an L. Okay. So now we put the whole thing together, and we have E times 2 pi SL equals to 1 over epsilon naught times minus KB. If I think about how this is going to be 2 pi L, and then here's 2 pi L. Okay, so I have minus KB minus K, and I'll just do it like this, minus KS plus KB, right? That's just these guys here. And these guys are canceling out here, it looks like. And, I'm sorry, I should have also canceled this out here. So we just have an E times an S here on this sign. Okay? And so E is going to be equal to minus K S over epsilon naught S. So S is canceled out. And I have minus K over epsilon naught. In other words, that E vector I know points in the S hat direction because of the symmetry involved in the problem. That was part of my assumption in here, was that it could come outside of the integral in other words, I knew that E had only S dependence. And it looks like we have minus K over epsilon naught in the S hat direction. Okay, so that's this E in region 2. Cool. Okay. Oops. All right. So there's my E in region 2. Okay. Let's do region 3. So region 3 is going to be outside of the whole thing. So going back to my picture here, region 3 is going to be S greater than A, right? So this is region 3. And here again I have 2 pi SL times E. That's my left-hand side of Gauss's law. Is equal to, now we're going to have a contribution from sigma A, from rho, and from sigma B. So I'm going to put 1 over epsilon naught, and I'll have my sigma A times 2 pi AL plus sigma B times 2 pi BL. And then I'm going to do the same basic integral here, and I've already done it, so I kind of know what it's going to be. I'm going to do minus K, this is going to be from the rho contribution, times A minus B, right? So it's basically like the last integral, but just instead of to some S, that S goes all the way out to A, times 2 pi L. Okay? So in other words, looks like I got 2 pi L's, 2 pi L's, 2 pi L's, 2 pi L's. So E should be equal to 1 over epsilon naught S times minus, Ka from this contribution, minus Kb from this contribution, minus Ka plus Kb. Interesting symmetry there. This and this are the same. This and this are the same. So electric field equals to 0. Okay. So electric field equals 0. So that means that that means that there's no actual charge that's enclosed for this problem. So that's interesting. No charge is actually enclosed because we're just dealing with a pure polarization. So I guess one of the things that we can take home from this is that when there is a pure polarization, in other words, when there's no kind of, let's say, other kind of charge distribution that we've sort of created or that we've put somewhere, then we're going to actually expect the total amount of charge to be 0. Okay, so let's see. We found the electric field, so we're done with that part, and then now we'll move on to the last part here, which is to calculate d using Griffith's equation 4.23. So I'll go ahead and just go to a new page for that. Let's see how to do this here. Okay. So I want to use Griffith's equation 4.23. So that says that d dot dA is equal to the Q free enclosed. I'm just writing it all out. So right, it's the enclosed free charges. But wait a second, there's not any Q and there's not any free charges, right? In other words, that means that D is equal to 0 everywhere. Okay. So let's think about that then. Okay, so then if I then use equation 4.21, so this is Griffith's 4.23. If I then use 4.21 equation, that says that D is equal to epsilon naught E plus P, right? Put some put some vector notation on here. Well, if this is 0, then that means that E is equal to minus P divided by epsilon naught. And if you remember, we were already given P, that for S less than B, P is 0. For S greater than A, P is 0. And for S is between A and B, then we just have that we just calculated the P, if you remember here, is minus K over S, right? So this is equal to minus K over epsilon naught S, right? So let's just verify that with something that we did before. So if I just look back a couple pages here to something I solved for that region 2, oh, maybe, hold on, what's going on? P should not be over S. Oh, I wrote down rho. Okay, I see what the problem is. So scratch that. So even easier, we didn't even have to calculate anything, right? Because we were given P, right? So P given in the problem was equal to K S hat, right? So if I just write in minus K S hat over epsilon naught, right, for my P that was given in the problem, then I actually get the same thing as I had gotten when I calculated for region 2. So this is a lot easier, right, of a solution than what we had done about the whole calculating the bound charges, both the surface and the density, volume charge density, that here we've actually just calculated directly based on recognizing that there aren't any free charges and saying, oh, okay, well then E and P are basically just related to one another. So that was a lot easier, right? So just thinking about D fields does have its advantages. D is not a thing. Like we can't actually measure a D, but it's something that ultimately contributes to what the actual electric field is. Hopefully that's been helpful, and please let me know if you like this video, these 2 videos, and if this is helpful, and if you'd like me to continue on this track of going through the homeworks in this way. Thank you.